The topics are up through conservation of linear momentum. So just the stuff that we've talked about so far. So any new stuff we talk about today is not going to be on the test. But remember, it's all cumulative, so you need to be ready to answer questions about the earlier stuff too. So let's start with any questions you have about, so I can answer questions on topics related to the test, or you know, questions about the homework you just did. Yeah. Yeah. Okay. Yeah. Anybody have the homework, the problems? I don't have them in front of me. Yeah, or I mean, I can take your computer too, but I just need to see what the problems are to go through them. Okay. Jill, do you have the paper? Oh. Okay. That's okay. Well, while somebody's pulling that up, let me all right, so there are two kinds of problems with conservation of linear momentum. Okay, so the two types of problems are inelastic. That's where the objects stick together. And in that one, you use the fact that mass of 1 times the velocity vector of 1 plus the mass of 2 times the velocity vector of 2. This could actually hold for more than 2 problems. You know, you could have m3 times v3 and so on. And this is all right before the collision. The instant right before they make contact is equal to m1 v1 plus m2 v2 right after the collision. And that's a vector equation, so that means there's 2 components. And so this gives you 2 equations. That was one of those things where I'm trying to think while I talk on autopilot, and what I'm writing doesn't make any sense. So we'll do it like this. They stick together, so after the collision, you have the 2 masses with a single velocity, and this is after the collision. And so you get 2 equations for 2 variables. Usually those 2 variables are the velocity vector of the combined thing after the collision. Okay. So you can solve for that without anything else. The second type is elastic collisions, the total kinetic energy is conserved. And in this one, we always have to know the line of motion. I think a good way to do this is set the x-axis along the line of motion. And your two equations are the first one says m1 times the x component of the velocity of 1 plus m2 times the x component of the velocity of the second one. That's before the collision. Is equal to, bless you, m1 times v1x plus m1 times v2x after. Okay, so that's the first equation. And the second equation says that the kinetic energy is conserved. So you have 1/2 m1 v1x squared plus 1/2 m2 v2x squared before the collision is equal to 1/2 m1 v1x squared plus 1/2 m2 v2x squared after. And so this is your two equations for two variables. It's different variables now. Probably, yes. Thank you. Okay, so the two variables are different in these two cases. For the inelastic collisions, if they stick together, two variables are Vx and Vy. There's only one velocity that we're worried about after the collision, and we can calculate both of those two components. For the elastic collisions, we're assuming that everything takes place in a line, so there's no, the way I have it set up here, there's no y component to the velocities after. And our two variables then are v1x and v2x after the collision. Yes. Yep. Okay, so, dang it.
So what are the two equations for elastic again? The M1, V1, and the 1/2.
Those are the ones that you can see right at the top there. So let's just go through a couple of these problems. Okay, so let's do number 3. That one has elastic and inelastic, so we'll just do both of them. So we have a train car with a mass of 2,500 kilograms and a speed of 21 meters per second collides with another one that's at rest with a mass of 3,000 kilograms. 21 meters per second, that's a bad collision. That's like close to 50 miles an hour. Yeah. Okay, so this one is 2,500 kilograms. And it's moving at 21 meters per second. And it runs into this other one that's at rest and has a mass of 3,000 kilograms. And we want to know, first, if they latch together. Well, that's sort of a gentle way of describing what's going to happen here. They're going to like both turn into powder. Yeah, exactly. So they latch together. So what's the combined velocity vector after? And then second, they bounce apart. What are the velocities after? Okay, so first of all, how much energy is this? This is unrelated to the questions, kind of. How much energy does that train car have before the collision? So the kinetic energy of that first car is equal to 1/2 times 2,500 times the speed squared. Can someone calculate that? 1,102,500. And what are the units?
Joules.
Yep, and we'll just call it joules. Yep. Kilogram meters squared per second squared. That's exactly right. And how fast would a baseball have to be going to have this much energy? Okay, well, so the way we'd set it up, I think the mass of a baseball is 0.145 kilograms. So 1/2 times 0.145 times the speed squared is equal to 1.1025 times 10 to the 6 joules. So can someone solve for V there? Oh, times 10 to the 6. Oh, yeah. The E is for exponent. It's just like a shorthand way of writing scientific notation. Okay, yeah. Don't be sure that you don't confuse that with 1.1025 times e to the sixth. That's a totally different thing, you know. Be sure you don't think of that as 1.1025 times e to the sixth power, you know, where e is 2.71 or whatever. That's a totally different thing. Yeah.
It's 3,899.60.
3,899
That's what I got.
meters per second. Okay. A little over twice that, so you know, 7,000 miles an hour or something. I think 2.24 times that. I did. What's wrong with it?
Yeah, that'd be like 8,735.
If we got a baseball and shot it that fast, we'd be able to knock it.
If they had an elastic collision, I don't know. I'd have to do that calculation.
So it'd have to stick to the.
That would be inelastic. So it would have to bounce off without losing any kinetic energy. I guess then. So then, yeah, if they bounce apart, kinetic energy has to be conserved. It doesn't really tell you anything. I mean, without doing the calculation. How fast do you think a baseball would have to be going to have the same linear momentum as that train car? Is it more or less than that? Way more. Yep. That's right. Okay, so let's do A and B. So part A, the inelastic collision. We're going to think of it from above. Okay, so we have this train car going 21 meters per second, and it runs into this one that's at rest. And so before the collision, we have 2,500 times the velocity vector of the first one is 21,0, plus the mass of the second one, 3,000, times its velocity vector before the collision, is equal to 2,500 plus 3,000 times the velocity after the collision. And that gives two equations. The x equation says, what's 2,500 times 21? 50,000 plus 52,500. Yes. 52,500 kilogram meters per second is equal to 5,500 Vx. And so what's Vx? $9.1. And then the y equation says 0 is equal to 500 Vy, so Vy is 0. So the velocity after the collision is 9.10. So now we're going to do the elastic collision where they bounce apart. So think about this. Think about this 3,000 kilogram car on the right. Is it going to be moving faster than 9.1 meters per second after the elastic collision, or slower? Any other guesses? That's right. Good intuition. It's going to be moving faster. Think about it this way. So, do you remember the last problem that we did last class? It's been a while now. The executive ball thing. And the way we did it was we had two things with equal masses. One started at rest and one had a velocity. Okay. So if this car had the same mass as this one, and this one started at rest and this started with a velocity, after an elastic collision, what would be the velocities?
0.
Yeah, this one would go to 0, and this one would be 21 meters per second. In an elastic collision, if they have the same masses.
I keep getting 9.554.
Okay.
Is that 2,500 times 21, right? Divided by 5,500.
It's 52,500 divided by 5,500.
Yep.
9.54. 55. Okay. Okay, so who's with me on this? So imagine that these are an executive toy. You have to have a big desk for your toy to have these numbers. But the idea is exactly the same as that executive toy thing that we did. If these have the same mass, it's exactly the same. Okay, so think this one's 2,500, this one's 2,500. And it has to be an elastic collision. And if it's an elastic collision, this one's going to come in, hit this one, this will stop, and this will take off with 21 meters per second. Okay. Well, this one is actually a little bit more massive in this problem. So there's going to be a little adjustment to what happens. What do you think is going to happen there? The one on the left is going to bounce back a little bit.
Which means by conservation of something or other, that the other one has to move faster.
Well, that's good thinking, except that this one has more mass. So it can actually, it has more momentum going this way without even having the speed of the original one. You know what I mean?
Oh.
Because it has more mass. So,
Yeah,
so this one will take off this way a little slower, I think, than 21 meters per second.
That's what I had
And
said
this one will
earlier.
bounce back.
That's what I had said earlier, and then you were like, no,
Sorry.
try again. I was like,
Really? Sorry.
yeah, okay. That's why I was confused. Be good now.
Okay. What would happen if this was 1,500? If this was less massive than that one in an elastic collision? Yeah, then this one would be moving this way a little bit after the collision, and this one would be moving that way probably a little faster. Okay. You see So with that in mind, like you can sort of have intuition about how these elastic collisions will work if one of these is starting at rest. Okay, think of it as an executive desk toy. Okay, slight modifications. Very ever so slight. Yeah, an executive train car toy. Okay, so now let's do the elastic calculation. All right, so we still have from above this one's going 21 meters per second. This one's at rest. Our coordinate system has the x-axis in the direction of the motion. So I'm only going to write down the, for conservation of linear momentum, I'm only going to write down the x equation. The y equation is always going to say 0 equals 0. So the x equation here says 2,500 times positive 21 plus 0 is equal to 2,500 times v1. That's the x component of v. I'll just write it as, I don't know, we can put the x in. And then plus 3,000 v2x. So we can write this as, well, divide everything by 2,500, and you get v1x plus 1.2 v2x is equal to 21. With me on that? Yeah, so the conservation of kinetic energy part now says 1/2 times 2,500 times 21 squared plus 0, anything that's not moving has no kinetic energy, is equal to 1/2 times 2,500 times v1x squared plus 1/2 times 3,000 times v2x squared. And we can divide everything by, cancel all the halves, divide everything by 2,500, and you get 21 squared is equal to v1x squared plus 1.2 v2x squared. What's 21 squared? Okay. Yeah. 441. Okay, that's equation 2 star. And now we have a system of 2 equations to solve for 2 variables. So let's do it like this. Star says v1x is equal to 21 minus 1.2 v2x. And so v1x squared, I'm just doing this so I can plug it in for v1x squared in equation 2 star, is equal to 441 minus, what's 2.4 times 21? 50.4 v2x plus 1.44 v2x squared. So now plug this into equation 2 star, and you get 441 minus 50.4 v2x plus 1.44 v2x squared plus 1.2 v2x squared is equal to 441. So those cancel. And you get 2.64 V2x squared minus 50.4 V2x is equal to 0. So you can factor, 2.64 V2x times the quantity. What's 50.4 divided by 2.64? 19.09 equals 0. So you get two solutions. V2x is equal to either 0 or 19.09. One of those matters to us. The one that's not before, exactly. If you got that on the test, that would be fine. I wouldn't take off points. If that was all you wrote and then you moved on to the next thing. But really, technically, we want to know what the velocities after the collision are of both of those two train cars. So plug it back in, and V1x is equal to, what do you get if you, negative 1.91 meters per second. So the other one, because it's lighter than the one that was last, bounces back a little bit. Yes, that's right. And the only so if you see a collision and you're trying to do the physics of what happens, you have to decide on two extreme possibilities. Either they, to come up with an estimate of what happens. Either they stick together perfectly or they bounce apart without losing any kinetic energy. Real collisions are somewhere in between those two. Any questions about that?
Yes, I do.
Okay, what?
The last problem first.
The one we-
Second to last problem. Yeah, with the ramps. Yeah. The ramps, the two ramps.
Okay. The vegetable?
Ramps.
Vegetable ramps?
Here's a tricky one. If a ramp is thrown out of the helicopter.
That's a good question.
Like some ramps.
Okay.
Ramps, scallions.
Doesn't it seem weird that computer companies haven't decided yet on which way the screen goes when you swipe? I know, but shouldn't there be an international standard by now?
There is.
What?
There's the regular standard, and then there's Australia or Moon.
They're upside down.
Oh yeah, because it's in the southern hemisphere. That makes sense. Now it makes sense. Okay, so you have the two carts and the two different ramps. I think that's the one you're talking about. All right, so you have a ramp there and a ramp there, and those angles are different. This one is 20 degrees, and this one's 30 degrees. And you have a 10-kilogram cart. This is another executive toy, could be. What? Yeah, maybe you change the angles or whatever, you know. A very busy executive. They need a lot of toys to play with. This one is 12 kilograms. And, you know, it asks a lot of stuff about accelerations and forces. So basically we want to be able to calculate acceleration of either one of those and any force that we want. Forces, accelerations. And I've said this before, but remember that anytime you use Newton's second law, you need to draw a free body diagram. And that free body diagram cannot be force vectors drawn onto the picture that I've drawn. It needs to follow the rules of free body diagrams that, you know, like in one of the lectures, I gave you a set of rules for free body diagrams. It's only an outline, no internal details, no external things drawn, and then the force vectors on it. So free body diagram of the 10 kilogram. What do we have? We have a weight down of 10 times 9.81. We have a normal force, N. And we have a cable tension, T. Yep, so any time you have a problem where a thing is rolling or sliding, when you isolate that body, you have the rotated coordinate system. So over here, our coordinate system is going to be like this. And for this one, it's going to be like this problem is a pain in a few ways, but one way is sort of nice. That's that because of the coordinate systems we're using, if this one moves an inch in the positive x direction, which way does that one move in its coordinate system? An inch in the positive x. So we can call those two acceleration vectors the same thing. We can just call them both A0. Okay. And so when we calculate the acceleration vectors of each of those two carts, it's going to look like they have the exact same acceleration. That's not exactly true because they have different coordinate systems. But the coordinate system of that, you know, the acceleration of the 10 in its coordinate system is the same as the acceleration vector of the 12 in its coordinate system. Okay, so force is 98.1 times cosine and sine of what angle for the 10 kilogram? 250. So can someone get numbers for that?
The top one is negative 33.55.
Okay.
And wait, doesn't the sign one not matter? The sign one's
Yeah, let's just write the whole vector equation, but you're exactly right. The sign one is not going to matter. And if you see that ahead of time, you can take advantage of that. I'm just going to do the full vector equation. Okay. And does it make sense that those are both negative? Yeah, because in the light green coordinate system, that's in the third quadrant. Okay, so Newton's second law says 0, negative, nope. It's not funny. Negative 33.55, negative 92.18. Yep. Plus T0 plus 0n. It wouldn't be true if this was a friction problem, because then you'd need the y component to calculate the normal. And all that's equal to the mass of 10 times the acceleration that's only horizontal, so I'll just write that as a0. And then the x equation says t minus 10a is equal to positive 33.55. And I'll set that aside. I mean, if I could solve it, I would just solve it and be done, but that's one equation for two variables. So we can't solve it. Okay? And now go to the second one.
How did you, oh, never mind, that makes sense.
As far as like whether you only write down the x equation or write down the full vector equation or whatever, if all of these problems are going pretty much right for you, you know, like you're not having too much trouble thinking about them and stuff, then yeah, it can save you some time to skip writing the full vector equations. But if this stuff is still challenging for you, just don't mess with that. You know, just be systematic about it. Write out the full vector Newton's second law. And then once you have it all in front of you, you know, you have something visually, you can see what's going to be useful and what's not going to be useful. So I would recommend, you know, I think when you get to the point that you can skip steps, it's sort of obvious to you, but don't, you know, don't start out by trying to skip steps until you start seeing patterns, you know what I mean? Just write out the full thing, get that stuff all down on paper, and go from there. Okay, so free body diagram for the 12. There's a downward force of 1177, I think, 0.2. Is that right? 1177.2 times cosine. So what's the angle? This one's 30 degrees, so it's going to be 270 plus 30. So this angle will be 300 degrees for the second one. The angles are different. This one. Yes. 117.72. Let me finish this free body diagram and then we'll get those components. So then we got this normal force. It's not the same as the other one, so maybe I should call this N2. But the cable tension is the same as the other one. What do you get for weight force? Positive 58.86. And then for the Y? Yep.
So is a single cable always
Yeah, as in our class, yes. If there's a single cable that only goes over pulleys, then the tension's the same all along the. In future classes, the assumptions that depends on are a weightless cable and a massless and frictionless pulley. If any of those things change that, but we always assume weightless cable, massless pulley, frictionless pulley.
Negative 101.
Okay, and then Newton's second law says, so that t is in the negative x direction, so negative t0 plus 0 n 2 plus 58.86 negative 101.95. And that's all equal to the mass of 12 times the acceleration vector of a0. G, did you say? Oh, I got. Yeah, so the x equation here is going to say negative t minus 12a is equal to negative 58.86. And that's double star. So now we have two equations for two variables. So if we add up star and double star, the t's go away. We have negative 22a is equal to, what's minus 58.86 plus 33.55? What?
It's like positive on the left side and negative on the right side for the acceleration? Or is it positive on those? Wait, is the acceleration the same?
So the way we set it up, we come up with a relationship between the motion of one and the motion of the other. And you can do that just by thinking about what happens if you move one and inch one way. What's the other one? In a lot of the examples we do, it works that way. But in this one, if you pull this one an inch in the positive x direction, this one goes an inch in its positive direction. So in this case, those acceleration vectors are the same.
And it would be going the right.
They'd both be going to the right, even though at slightly different angles. But in their own coordinate system, they'd just be going in their own x direction. Yep. So A is 1.055 meters per second squared. And then you can calculate T. What do you get for T? Newtons. And it makes sense that, intuitively, you know that they're going to be moving in their positive x directions. Okay. Okay.
It is 1.15.
Okay, 1.15. And then plug that back in for T. What? 45.05. Okay, so if you look at this problem,
But would the tension be positive?
tension is always positive. But if you think of it as force vectors, then those are different. Now, if you want to find the force vectors the cable's applying to each one of those, take that 45.05 and plug it into the force vector that you used in Newton's second law. So on the 12 kilogram, it would be negative 45 and then 0. On the 10 kilogram, you plug it in here, it would be positive 45, 0. And if you look at the original problem, the answer, the directions that we got for stuff make sense with what we can pretty clearly see is going to happen. This is steeper and it has the more massive object. So this is going to pull the other one. This one's going to go down and pull the other one up. So we know the accelerations are going to be in the positive x directions. Okay, let's take a 10-minute break. Come back at 5 minutes to 9, and we'll do a conservation of linear momentum problem at the board. We'll just do a new one, yeah.
That was like the best possible answer you could have.
As you wish. Okay, so let's say we got two cars. This one's going 5 meters per second and has a mass of 1,000 kilograms. And it runs into this other car that has a mass of 1,500 kilograms and is going 4 meters per second. What are the final velocities? After, so first we'll do inelastic, and then I'll do that one, and then you'll go back and do it for elastic. Okay, so how could
These are some like wind stuff.
yeah, it is.
Just a little feet coming out.
No. Okay, so yeah, see if you can do that. How would it become inelastic? Like, you know, maybe their bumpers would lock together or something. You know, that can happen in collisions. So see if you can go through that. So for the elastic case, so conservation of linear momentum. Remember, that's a vector equation, so you have to include the directions of the motion. So we have the 1,000, you know, for the x equation, we have the 1,000 kilograms times, what was the velocity of that one, 5? In the positive x direction, plus the 1,500 kilograms times the direction, the velocity of -4. Okay, if you don't have that negative in there, it's going to be wrong. And then that's equal to 1,000 V1 plus 1,500 V2. divide everything by, well, what do you get here? 5,000 minus 6, so negative 1,000 is equal to 1,000 V1 plus 1,500 V2. And so you get V1 is equal to negative 1,000 minus 1.5 V2. Nope, this is 1. V, yes. Did everyone get that?
Do I have to use V1 and V2? Can I use VA and VB?
Yeah, sure. And then conservation of kinetic energy says 1/2 times 1,000 times V1 squared. Well, we know what that is before the collision. That is 5 squared plus 1/2 times 1,500 times negative 4 squared. The negative isn't going to matter in this one because kinetic energy doesn't have direction, so all that matters is the speed. And that's equal to 1/2 times 1,000 V1 squared plus 1/2 times 1,500 V2 squared. Divide everything by 1,000 and you get 25 plus 16. 16 times 1.5 is 24 is equal to V1 squared plus 1.5 V2 squared. So 49 is equal to V1 squared plus 1.5 V2 squared. Which one? Yeah, right. Okay, so V1 squared is 1 plus 3V2 plus 2.2, 2.25, 1 point, yeah, 2.25 V2 squared. And so you get 49 is equal to the quantity 1 plus 3V2 plus 2.25 V2 squared plus 1.5 V2 squared. And so 0 is equal to 3.75 V2 squared plus 3V2 minus 48. Quadratic formula. Any of you have like a TI 89 or an Inspire that solves that? So V2 is equal to, well, one of its solutions is going to be negative 4. And then the other one is what? Positive? From this or from yours? Okay, so say it again. What did you get? Positive 3 point what? Okay, this one is what was happening before the collision, so get rid of that one. And the one we want then is 3.2. And then you can plug it back into like equation star, and what do you get for V1? What's negative 1 minus 1.5 times 3.2? 4.8. So negative 5.8. Thanks for the help, by the way. Losers. Okay. Any questions? All right. Well, I guess let's stop there. Test on Wednesday, so don't forget.